Hi, everyone. My name is Alex Hanson. I'm with the University of Texas at Austin. This video was originally created as part of a broader curriculum that was sponsored by Texas Instruments. I'm very happy to be able to share it with you now through the IEEE Pels tube. I hope that you will find this video useful in the design of power converters. Hi, everyone. I'm Alex Hanson, and in this video, we're going to look in detail at how to design a switching loop. We'll first recall that a switching loop has a very high priority in power converter layout. And in fact, I advocate that it be the first thing that you lay out in a power converter and that you design everything else around the switching loop. We'll take a quick look at where the inductance comes from in a switching loop, and we'll see that good switching loops minimize the loop area, which is pretty much something that everybody does, but they also maximize the loop's depth. And you'll see what I mean by that and why that's so important in just a few minutes. We'll also review some very specific loop layouts, and we'll find that so-called vertical loops have a lot of advantages over planar ones. And again, that vocabulary will make sense in a few minutes. For the moment, let's just review why this is so important. Let's consider a boost converter where we have a voltage source and an input capacitor. We have an inductor and a MOSFET and a diode. And finally an output capacitor before encountering the load, which I'm drawing as a resistor, but it could be anything. And without even thinking about all of the digital components, the microcontroller, the gate driver, let's just consider all of the loops that are present in the power converter itself. Doing mesh analysis, we can analyze the current flowing in different loops, I1, I2, and we can do this for each one individually and see if that helps us identify which loops are going to be high priority. Now, all of these loops are going to involve voltages and currents that are on the same order as the input and output voltage and the input and output current. In other words, main power stage current. So comparing these loops based on power is probably not going to yield a lot of results, but we can compare these loops based on frequency. So let's go ahead and draw our frequency spectrum here. And let's talk about components that are at or near the switching frequency. We'll talk about components that are at harmonics of the switching frequency. And then there are components that are substantially below the switching frequency. This is either DC or low frequency. I'm going to argue, first of all, that I1 and I4, or the loops associated with I1 and I4, carry primarily low frequency content. The main current coming out of the voltage source is going to be low frequency, as is the main current going into the load. And of course, this is by design. This is how we want it to be. The current flowing in loop 2 does have switching frequency components to it, so I'll put I2 over here. However, I2 is a continuous current. We know this because I2 is equal to the inductor current, and inductor currents must always be continuous. And you might say that I2 flows through the switch and the switch turns off and on, but remember that the switch current is the difference between I2 and I3. And so I2 can be continuous and I3 may be discontinuous while still having the MOSFET current being discontinuous. So I2 is a continuous signal, so it has components at the switching frequency, or maybe including a few harmonics of the switching frequency. And so that actually is a reasonably important loop. However, I3, the current flowing in through that loop, is actually a discontinuous current. So it not only has components at the switching frequency or nearby, it has components at much higher frequencies as well. And again, this is because I3 is discontinuous. And I3 is discontinuous because of these switches that are turning off and on. And so the loop that I've labeled I3 is our winner. That is, in most power converters, the most important loop to lay out. This loop I3 is very frequently known as the switching loop because it involves the two switches and the capacitor. And the switching loop almost always looks like this. It's almost always two switches and a capacitor. So we know which loop takes priority. This loop consists of, at least in this circuit, a MOSFET, a diode, and a capacitor, three components forming a loop. And we're trying to form them in a way that minimizes the parasitic inductance of the loop itself. The question, of course, is how do we do that? Analyzing arbitrary structures in space is very difficult, and we can typically only solve them by hand when they're highly idealized. So I'm not going to pretend to give you a method for solving for the inductance of different kinds of arbitrary loops. Instead, I want you to consider a very, very simple situation just so we can come to a conceptual realization. And in my mind, the prototypical example of an inductor is an air core solenoid. So I'm going to draw this wrapped around, for example, a plastic bobbin, but it needn't be. So here comes my solenoid. It's just a coil of wire wrapped in a vertical configuration. And so long as that coil is very, very long, ideally infinitely long, this becomes a tractable problem to solve. And again, we're considering this for a non-permeable core like plastic or just air, but it's easier to visualize with some sort of former to wrap around. Now, we've all done the long solenoid problem back in physics classes, and we calculate that the inductance L is equal to mu naught n squared, and we always remember that inductance is proportional to n squared, multiplied by the area of the coil, and the area would be the cross-sectional area that the coil wraps around, A, divided by what I'm going to call the depth of the coil, D. And the depth is this dimension here. Now, of course, for a parasitic loop, we're not going to intentionally go wrap a whole bunch of turns. So n squared is always 1 when we're dealing with parasitics. We're also not going to intentionally put any magnetic material in there. So if there were some relative permeability, that would almost always be 1. Which leaves us with just the geometry. Now, for some reason that I can't fully explain, almost everyone remembers the area part. They say, hey, if you want to design a loop that has very low inductance, you gotta shrink the cross-sectional area. And they put all of their components very close together, and that's totally correct. That is a good thing to do. But again, for reasons I can't explain, I find that people tend to forget the depth part of this equation. In other words, how tall the loop is, at least the way I've drawn it, matters a great deal. And it can be useful to look at parasitic loops kind of like one-turn solenoids. So for example, suppose you have a printed circuit board, and you draw a track, a circular track, on the top layer. Well, that track might look something like this, and current's going to flow around that track, like so. The area that we're talking about for this track would be this area here, and maybe including some of the copper, depending on if we're skin depth limited or not. That would be the area, and that's the part that everyone remembers. But what would the depth be? The depth would just be the thickness of the copper that you use to form this loop. So while you've done a good job of keeping the area small, you've inadvertently made the depth extremely small. And that has the tendency to create large inductances. Now conceptually, compare that to a different kind of a loop. Imagine taking a ribbon of copper, wide and flat, and folding it back on itself, like so. So here's my ribbon of copper, and I've now folded it back on itself. So current's going to flow this way. It's going to round the curve here on the copper, and it's going to return on this layer, and I can't draw more arrows because I've hidden most of that copper. Now I haven't drawn this as a complete loop, but we can complete the loop if we wish. Now what are our variables in this case? Well, our cross-sectional area would be this area here. It's the area that the current wraps around. And you can do a good job of keeping that small. But now in this case, what is the depth? The depth is this dimension here. From there to there. That would be the depth. So while on the top case, the depth might be on the order of microns, in the bottom case, the depth could be on the order of millimeters. And that's a factor of 1,000 different. And if we can keep the depth from being too small, we'll keep the inductance to a much more manageable level. Now, one quick pointer before we move on. I don't want you going and using this expression to try to calculate parasitic inductance. This equation is only good for an infinite solenoid, and both of the shapes I've drawn at the right infinite solenoids, they are not. So the inductance you'll find isn't actually well predicted by this equation. But what we do get out of this is a much more intuitive understanding of the role that area and depth play in determining the inductance of a structure. Now, in order to let us look at some concrete methods for designing switching loops, I've gone into KiCad and created 3 identical switching loops, or identical from the schematic point of view at least. They each consist of a MOSFET, a diode, and several small capacitors, and you'll see why I've broken up what electrically is one big capacitor into several small capacitors in a moment. But let's just take a moment to appreciate that from a schematic point of view, these are all exactly the same. I'm using the same components, and you'll see in a moment I'm using the same packages in all 3 cases. But you'll see that the layouts are quite different, and I promise if you went and built those layouts, you'd see rather different results. So here are the 3 layout examples that I want us to consider. The first is called a planar loop, and the second 2 are both called vertical loops, but they're slightly different from one another. Now let's try to understand the planar loop first. The planar loop very closely resembles what I described before. We've put all of our components, including our MOSFET, our diode, and our capacitors, all on the top layer, and we've connected all of them to each other on the top layer. And this is why it's called a planar loop, because the loop all takes place within a single plane. This is possibly the most common kind of loop seen in power converters, and almost every application note out there will advocate that if you lay out your components this way, that you shrink the area of the relevant loop, which you can see we've done here. The area is about as small as it can be. Nevertheless, by virtue of being a planar loop, the depth of the loop, as I'm calling it, is very, very small. It's only the thickness of the copper, or in some areas, the thickness of the components. So we actually expect this loop to yield fairly high inductance. And by now, you can probably predict that I consider this to be the worst of the 3 layouts. Vertical loop 1 is a very, very different kind of loop. Here we've put the switch on the top layer and the diode and the capacitors on the bottom layer as so. Now this much more closely resembles the second loop I showed on the previous slide. We have a wide, ribbon-like path for current to flow in, and the return path for the current flows right underneath the original path. This loop also has a small area. The height of the cross-section is just the height of the printed circuit board, and it's only as long as the components are, so that loop isn't terribly large. So just as in the previous case, we've kept the area small, but the big difference here is we've made the depth much, much larger. Vertical loop 2 is another alternative that seeks to achieve the same thing. But here, rather than put the diode and the capacitors beneath the MOSFET, we've put them all on the top layer. However, unlike in the planar loop, we're not going to connect all of the components on the top layer. Rather, the current flows in a straight line involving the diode, the MOSFET, and the capacitors, and then the return path, just like vertical loop 1, returns right underneath that original path. The advantage of a layout like this is that instead of using the backside of the circuit board for the return path, we can use the second layer in a 4 or more layer board. Now the way KiCad draws this is it draws the top layer and the second layer and the third and the fourth all being equally separated from each other, but in a real circuit board that's not typically true. Generally speaking, the top layer and the second layer are very, very close together, as are the third and fourth layer. And there's a pretty big separation between the top 2 and the bottom 2. So the height of our loop, if we can call it that, in this vertical loop 2 is less than a quarter of what it was in vertical loop 1. And frequently, this vertical loop 2 will yield an even smaller inductance. So as you can imagine, I don't recommend using the planar loop. But I don't necessarily recommend the vertical loop 2 in all cases either. And vertical loop 1 and vertical loop 2 both have distinct advantages. One advantage of vertical loop 1, for example, is that you have vias coming down on both sides of the MOSFET and on one of the sides of the diode. And so if you design this loop right, you can get pretty good thermal dissipation on both of these high power components. With vertical loop 2, however, this is virtually impossible. Because of the way the return path is drawn, at least one of the two switching components is not going to be able to have vias going down right below it for heat sinking purposes. Vertical loop 1 also has easier access to more of the nodes. For example, both the source and the drain of the MOSFET are easily accessible by the external circuit. With vertical loop 2, however, it's a little bit trickier to access some of those other nodes. Nevertheless, typically vertical loop 2 will give you the absolute best parasitic inductance that you can hope for. And so depending on your circumstance, you may choose one or the other of these two switching loop layouts. Okay, so that's our tutorial on laying out switching loops. We reviewed that because a switching loop has the highest combination of frequency and power in the power converter, it gets very high and, in my opinion, the very top priority when doing power converter layout. We saw that the depth of a loop plays just as much of a role as the area of a loop in determining the inductance, even though the depth is often ignored. And we reviewed conceptually how to achieve a quote-unquote deep loop that also has small cross-sectional area. And finally, we specifically reviewed planar and two different flavors of vertical loops. And we advocated for avoiding the planar loops while embracing one or the other of the vertical loops, depending on how important things like thermal management and access to different nodes are in a particular circuit. And I use both kinds of layouts quite regularly.